Welcome to you all to this MOOCs online video course Theory of Yarn Structure. Today we are going to start module 9. This module talks about strength length relation in yarn. All of us know that usually yarn strength measurement is carried out at a gauge length of 500 millimeter, and based on our experimental results we predict what will be the behavior of yarn during subsequent manufacturing stages. However, in post spinning operations yarns experience stress at gauge lengths other than 500 millimeter. For example, in warping the length at which a yarn is stressed is approximately a few meters. On the other hand, in weaving yarns experience stress at a very small length, a few millimeter. What is the use of then 500 millimeter gauge length while testing the tensile strength of yarn? So, it is quite clear that the strength measurement on yarn at 500 millimeter gauge length is not sufficiently enough. We need to find out the strength of yarn at different gauge lengths. However, this is very difficult. Is there any theoretical expression available that can predict the strength of yarn at different gauge lengths? That was a question long ago, and the scientist Frederick Thomas Peirce in the year of 1926 developed a theory on yarn strength dependence on gauge length. Today we are going to discuss Peirce theory on strength length relation in yarn. This theory is based on a very interesting imagination. What you see here is the left hand side, there is a chain, long chain consists of several links. How many links you can see here? 6 links are shown, 1, 2, 3, 4, 5, 6. Out of these 6 links, the link which is shown by double lines is the weakest link. So, if we apply a force say S, then at which force this complete chain will be broken? So, when we apply force onto this chain. As this link is the weakest link, this will break first. The moment it breaks, the entire chain breaks. So, the strength of the entire chain is decided by the strength of its weakest link. This is the principle of so called weakest link principle. This principle was used by Peirce while developing his theory for strength length relation in yarn. Now, when this link is broken, obviously the other links are not broken. That means this link has the lowest strength, but all other links have at least a strength higher than the strength of this link. So, if we individually measure the strength of all links, then the average strength of all links must be higher than the strength of the chain. So, the average strength of the links is much higher than the strength of the chain. This indicates that if the length of the chain increases, its strength decreases. This concept was utilized by Peirce. So, on the right hand side, what you see is that a long length of yarn L is divided into many parts of small length n parts, each length L subscript L. So, capital L is equal to n into L naught, and here again we apply force S. So, what will happen? Out of these n parts, there must be one part which is the weakest. So, that part will be broken first. As a result, the entire long yarn will be broken. So, the strength of the yarn, that is the maximum force at which yarn breaks, is equal to the strength of the weakest part of this yarn. So, this is basically the principle of weakest link. So, that was the starting point of Peirce theory. Now, we will discuss about this theory in a more detailed form. So, this model we will discuss now. Yarn strength is a random variable. Let us consider that the probability of breakage of a yarn of length L at a force S is F S and L. So, the probability of breakage of a yarn of length L at a force S is this. This is the probability. So, this probability must lie from 0 to 1. What is the sense of 0? What is the sense of 1? So, let us discuss that now. S has a minimum value S minimum and also has a maximum value S max. So, this S has a minimum value and a maximum value. If the force is less than S minimum, yarn will not break. On the other hand, if the force is greater than S max, yarn is broken. This can be written in terms of mathematical language in this form. So, the probability that S is less than S minimum is 0. Similarly, probability that S is greater than equal to S max length L is 1. So, this FSL has a sense of distribution function. What is distribution function? If you open any basic book on probability statistics, you will realize that a random variable is characterized by probability characteristics as well as statistical characteristics. The probability characteristics include two functions. One is called probability density function PDF, the second is called cumulative distribution function CDF. This cumulative distribution function is also called as simply distribution function. So, here this FSL has a sense of that distribution function. Now, this is the probability that a length L will be broken by applying a force S. What is the probability that the length will not be broken, the length L will not be broken by application of this force S? That is called complementary probability, that is 1 minus this probability. So, probability of survival, that is the probability that a yarn of length L will not be broken by applying a force S is complementary probability. Right. So, the probability of survival is 1 minus FSL. Suppose the probability of breakage of a length L is at a force S is 0.8. So, what is the probability of survival? Probability of survival is 1 minus 0.8, that is 0.2. Right. Now, Peirce strength model is based on 3 important assumptions. We will now discuss those 3 important assumptions now. Peirce first assumption. Look at this right hand one diagram. This long length is L, short length is L naught, L subscript 0. The probability of breakage of any short section or short part is independent to the probability of breakage of any short parts or short sections. That means what? That means if suppose any of these n parts is broken, that breakage will not influence on the breaking of any other parts. So, the probabilities of breakage are independent. So, Peirce's first assumption was the probability of breakage of any small part or section is independent to the section. So, the probability of breakage of any small part is independent to the probability of breakage of any other small part. So, this was the assumption of Peirce, independent probability. So, breakage of one section will not influence on the breakage of other section. Then he introduced his second assumption. His second assumption was also related to this diagram. The longer section of length L must not break until any of these small section of length L0 breaks. That means, this long length of yarn will sustain until and unless any of the short section or short part is broken. This is the principle of weakest link. So, the second assumption was the longer length section of length L must not break until any of its shorter section of length L naught breaks. So, the longer section must not break until any of its shorter section breaks. This is the principle of weakest link theory. We will introduce Peirce's third assumption a little later. Before that, we would like to see what will be the consequences of these two assumptions. Let us find it out. Consequences of these two assumptions. What is the probability of survival of this long yarn 1 minus F S L? So, this long yarn is survived until all short sections are survived, and the probability of survival of all these short sections are independent. So, we can write that the probability of survival of the long yarn of length L is equal to the probability of survival of first section multiplied by probability of survival of the second section of same length at that force S multiplied by probability of survival of the third section and so on of the nth section. As these probabilities are independent, so they are multiplied. So, two assumptions are used here. So, we can write this n times. So, we write this as 1 minus f S L to the power n. What is n? N is L by L naught. So, 1 minus f L by L naught. Right. So, we can write it further. L naught. So, this is how these two probabilities are related. So, this equation is a very interesting expression. Using this expression, later on you will see how we obtain the probabilities. Now, also we can write one more thing from here. This is about the survival. What is about the breakage? We can also write probability of breakage of a longer length L at force S is equal to 1 minus to the power n, or we can write by substituting L as to the power L by L naught. So, this expression is also important. You will see, if we know this probability, then we will be able to find out this probability. So, the probability of breakage of smaller section is known, then by using this relation we will be able to find out the probability of breakage of the longer section. So, this was related to the distribution function. As I already told you, probability characteristics of a random variable are often expressed in terms of two functions. One is the distribution function, second is probability density function. So, we will now speak about probability density function. In short, it is known as PDF. So, probability density function of longer length L, as it is known, it ranges from 0 to 1. How these two functions are related? These two functions are related using this. So, a probability density function can be found out by differentiating the distribution function with respect to the random variable. Analogically, for f s L naught, f naught s. What is the difference between these two? The difference between these two is here it is L and here it is L naught. Okay. Now, we use this expression to find out the PDF, how these two PDFs are related, right. So, f s L is the this, and what is f s L? Write down that 1 minus to the power zero, right. This is clear. So, what will be the differentiation? The differentiation will be L by L naught 1 minus this L by L naught minus 1 into delta f naught by delta s, isn't it? What is the last term? This last term is this, isn't it? So, this is equal to f into 0. So, PDF at long length is equal to L by L naught into PDF at short length into 1 minus f s L short length L 0 minus 1. So, this equation is also an important one because it relates the two PDFs, one associated with the long length and the other is related to the short length. So, what we did? We introduced two assumptions of Peirce. Based on these two assumptions, we are trying to correlate the relation between two distribution functions and the relation between two probability density functions. So, earlier we have established this relation between two distribution functions, one is associated with length L longer and the other is shorter L naught, and here this relation gives the association between two PDFs, one is at longer length, the other is at shorter length. So, this is the consequence of Peirce two assumptions. Now, we will introduce Peirce third assumption. What is Peirce third assumption? Peirce third assumption, let us now introduce. So, why this third assumption is required now? Try to understand. If you know the probability of breakage at smaller section, you will be able to know the probability of breakage of longer section. Ultimately, what is your aim? Your aim, based on small length data, you try to predict what will be the strength of longer length, because it is easier to obtain the strength of longer smaller sections experimentally. So, Peirce third assumption was related to the probability of strength of shorter sections. So, what is the Peirce third assumption? The strength of shorter specimen of length L naught follows Gaussian, the so called normal distribution. With normal distribution with mean. Normal distribution is a two parametric distribution, mean value and variance or standard deviation, with mean at this and standard deviation positive square root of variance at sigma naught, right. So, this was the third assumption of Peirce, Gaussian distribution. Right. So, we know the probability density function of Gaussian distribution. Show the PDF of strength of shorter specimens. The PDF is a normal distribution. So, f SL naught is equal to 1 by root 2 pi into 1 by sigma naught e to the power minus random variable minus its mean value square into 2 sigma naught square. Right. So, this is the PDF of Gaussian distribution or normal distribution. Right. Then what is the distribution function? This is the PDF, and what is the distribution function? Of strength of shorter specimens. Right, we all know the distribution function of normal distribution, that is your in this case FSL naught, starting lower limit is minus infinity to that value. What is that value? Capital S. So, that is why we have to use some other symbol, say Q of L0 dq. Right. So, if we substitute here, as we have used this symbol here, the value, that is why you have used some other than S here, Q. So, what is that value? So, this is 1 by root 2 pi sigma naught, right. This is constant and then integration starts minus infinity to S to the power minus S. So, not S here, it will be Q here, Q minus S naught square by 2 sigma naught square, and the variable is into right here into dq. So, if you solve this integral, you will be able to know about the distribution function of strength of shorter specimen. Right. Now, what we have to do is quite clear. Now, we have to basically find out the PDF and distribution function of strength of longer specimens. Before doing that, we would like to use standardized Gaussian distribution, because it is easier to work with standardized Gaussian distribution. So, let us use that standardized Gaussian distribution. Let us assume that a random variable u follows the standardized Gaussian distribution. Then what is the PDF of u? PDF of u is phi u. Phi is here expressed in lower case. Okay. So, this is well known 1 by root 2 pi minus u square by 2, right. And what is the C distribution function? Of u? We use uppercase of phi, u is equal to minus infinity to u. So, we have to use some other phi lowercase dv. Okay. So, how we write out? So, let us express this 1 by 2 root over 2 pi will come out of integration, they are constant. So, minus infinity to u, then to the power minus v square by 2 into dv, right. So, these are the PDF and distribution function of u. Now, we can using this we can write the earlier expressions in some different forms. So, this expression we can write in terms of standardized variable. So, let us see how we can write f s L naught. What was the expression? 1 by root over 2 pi into 1 by sigma naught minus s naught square to sigma naught squared. That was the expression. So, what do we do? We take this out, 1 by root 2 pi minus square to this. Now, if you compare this with the standardized PDF of u, this is this. So, when it is u here is u here. So, we can write this as 1 by sigma 0 into lowercase phi s minus s naught by sigma naught. Okay. So, if we compare, we can write this expression. So, what will be then this distribution function? Distribution function f s L naught. So, minus infinity to s, what was that earlier? Earlier this was this minus infinity to s f q L 0 dq, right. So, we are trying to write down the same f q L 0 dq, right. So, what was that? 1 by root 2 pi sigma naught minus infinity to s exponential minus q mean value to sigma square dq. So, we will write this. One by root over 2 pi into 1 by sigma naught integration minus infinity to s to the power minus q s naught square 2 sigma square, right, into d q. Earlier expression, it is dq here. Now, if we substitute say q is equal to sigma naught v plus this, and so if we have this substitution, then what is dq? dq is sigma naught into dv. So, we can further write is equal to 1 by root 2 pi, right, and so dq by sigma naught is dv. So, minus infinity. Now, where it is s, so v will be s minus s naught divided by sigma naught, s minus s naught by sigma naught, potential minus v square by 2 into dv. What is this? This is uppercase phi s minus s naught by sigma naught, right, clear? Okay. Now, what do? We now put up a question. The question is as follows: what will be the distribution of strength of longer specimens if the distribution of strength of shorter specimen is Gaussian? So, let us write down our question. What will be the distribution of strength of longer specimens when the distribution of strength of shorter specimens is Gaussian. Will it be Gaussian or will it be something else? Let us try to find out that. So, you remember our earlier expression 1 minus FSL is equal to 1 minus F L naught to the power L by L naught, right, and what was your FSL naught is this. So, this is equal to uppercase phi s minus s naught by sigma naught. Okay. So, we write down 1 minus s minus s naught to the power L by L naught, right. So, what is FSL is equal to 1 minus uppercase phi L by L naught. So, this is the distribution function of strength at longer length. What will be then the probability density function of strength of longer length? Let us now find out that. That also we have generalized earlier, that is here. No, this is here. So, this is the relation between PDF of longer length to the PDF of shorter length, PDF of longer, PDF of shorter. So, you use this expression, we use this expression. So, F S L is equal to L by L naught F naught into 1 minus F to the power L by L naught minus 1, right. Now, what is F S L naught? This is here, this is here. So, 1 by root 2 pi 1 by sigma 0 exponential this. So, if we substitute this, what we will obtain? L by L naught 1 by sigma naught, then phi by sigma naught, right, and into 1 minus phi to the power minus 1, right. So, this expression characterizes the relation between two PDFs, one is associated with longer length and the other is associated with the shorter length. When the shorter length distribution is Gaussian, then this will be the distribution for PDF for longer length, right. What we see is that if L is not equal to L0, then the distribution is not Gaussian, because Gaussian distribution has a standard form of PDF, but this standard form of PDF will obtain only when L is equal to L0. In all other cases, the distribution is not Gaussian. We will graphically show it to you later on. Now, we discuss about the some standardization. Sometimes strength S at length L is transformed as follows. Look at carefully the word transformed. We have not used here the word standardized. Standardization was related to the small length, but for longer length it is transformation. What is this transformation? This transformation what do we do? Now we will now discuss about this transformation in the next class. Also we will discuss about the probability characteristics for this class, probability characteristics and also statistical characteristics of random variable. So those we will discuss in the next class. Thank you for your attention.